Math over here, and this is the 2020 SMT Discrete Math section problem number 5. Here's a view of this problem. Find the smallest integer value of n such that 2 to the 2 to the 2 all the way until the last 2, which is n2's, is greater than or equal to 16 to the power 16 to the power 16 to the power 16. Alright, so over here we have two enormous numbers, and we want to find the least number of 2's necessary to satisfy this condition. So let's maybe rewrite this. 2, 2, all the way diagonally, and then over here what we'll have is we'll have n 2's is greater than or equal to 16 to the 16 to the 16 to the 16. Okay, so when I see a tower of powers, what I want to do is I want to take a logarithm, right? Because a logarithm will kind of simplify it, because we know if we take an appropriate base logarithm, we can, the exponent can jump out, and then we can simplify it maybe a little. So taking log base 2, we get 2 to the 2 to the 2 all the way up to the last 2. This time, since we're taking log base 2 of 2 disappears and this exponent jumps out. We now have n minus 1 2's. This is going to be greater than or equal to, if we were to take log base 2, then we'd get the 16 to the power 16 to the power 16 as the exponent jumping out, and then log base 2 of 16 is just 4, so times 4. Okay, so this is good, but let's try to do it again. I know I can do this again because, well, we'll just repeat the same process over here, and to the right we have a log AB, which we can split up even further, plus we have nice powers of 2 to do so. So again, taking it again, I'll just do it over here. Taking it again, we should get 2 all the way to 2. This time we already know it's going to be n minus 2 2's. N minus 2 2's is greater than or equal to, now if we were to take log base 2 of this, the 16 to the power 16 jumps out. 16 to the power 16 jumps out. We're left with log base 2 of 16, which is times 4, and then plus log base 2 of 4, which is just 2. So now this is just absolutely amazing, right? Because we have 16 to the power 16, we have 4, which we know we can both express as powers of 2's, and we can combine those. So we have an inequality which is easily solvable. So just like reiterating, greater than or equal to 16 to the power 16 is the same thing as 2 to the power 4 to the power 16, which is 2 to the 64th. Now if we were to multiply 2 to the 64th times 4, that's 2 to the 64th times 2 squared, which is 2 to the 66th. With the plus 2 over here, which is rather insignificant when comparing to 2 to the 66th. So now really the only question is, how many 2's is sufficient to guarantee that this power tower is greater than or equal to 2 to the 66? So now all we have to do is experiment a little. So say this enough. This is just 2 squared is 4, so this is just 2 to the 4th. That's not enough. So suppose we were to have this. This would be 2 to the 4th, which is 4, and then 2 to the 4th, which is 16. So this is finally 2 to the 16th. Still not enough. So, but once we get to 5 2's, we have 2 squared, which is 4, and then 16, and then 2 raised to the power 16, which is already a whole large number on its own, and then we're raising 2 to that very large power of its own. This is obviously going to be much greater than 2 to the 66 plus 2. So now we know that this power tower has n minus 2 2's, and in this case n minus 2 would then be 5. So solving for n, we simply get n equals 7. And we are done.